So the topic today under discussion in this video is PDPs. PDP stands for Power Delay Profile. This is a video by Hassan Khan and Ahmed Feroz Khan. So, what is PDP? The Power Delay Profile gives the intensity of a signal received through a multipath channel as a function of time delay. So, PDP profiles usually give us a lot of helpful information on different types of channels, and those multipath channels could be the channels which are receiving different kinds of delays, signal delays due to reflection, scattering and diffraction. Going on to what is time delay. Time delay is the difference in travel time between different multipath arrivals. So when a signal is transmitted, it is received in different time periods, which we call different multipaths, and that is due to different obstacles within the transmitter and the receiver. So our signal comes in small chunks and it is delayed as well. So there are different units of time delay such as ABSCA and decibels. We most commonly use decibels. So what is the purpose of PDPs? PDPs are essential for modeling of channels facing small-scale fading, and these PDPs can be characterized with these helpful parameters such as mean access delay, RMS delay spread, and the coherence bandwidth. Here is a picture of a normal PDP. As we can see, the RMS delay spread has been calculated through a formula which is usually given, and mean access delay and the maximum access delay. These are quite helpful in determining our channel and what type of channel do we have, what kind of fading or small scale fading or large scale fading our channel is facing. Here is another chart which shows our transmitted signal at the transmitter and our received signal at the receiver. So as I was saying before, the signal transmitted is received in different times at the receiver, such as T0, T1 and T2. And this table below is usually the different empirical values which are given with or calculated with the PDP profiles. These values also give quite the information of the different channels. So, recognizing the channel from time delay parameters. So, parameters such as RMS delay spread, as shown down below, has different two formulas, one for 90% coherence bandwidth and one for 50% coherence bandwidth. These help in calculating the coherence bandwidth, and once the coherence bandwidth is calculated, we can simply compare it with the signal bandwidth and make a decision on the channel. So, I will discuss a few PDPs to give you an idea how do PDPs help us in determining the channels. So the first one is the measurements and the wideband channel characterization for overseas propagation, and the other is the industrial indoor channel. So coming to the first channel, it is a power delay profile of a mobile channel for above the sea propagation. So for this channel, the measurement frequency is kept at 1.9 gigahertz and the height of transmitter and receiver is kept at 8 meters. The difference or the distance between the transmitter and receiver is varying between 40 to 14,000 meters. And these transmitter and receivers are kept on a boat, and the boat speed also varies from 0 to 22 knots. During this measurement, the transmitter antenna was also located at the fixed point at 21.5 meters above sea level, while the receiver was mounted on a boat moving along different routes into a harbor. So here are two pictures. The left side one shows the PDP profile of this channel, and the right side one shows the log normal graph of the channel, which shows the large scale fading prospect of this channel. So we can easily give a view of the large scale fading by the path loss, which can be easily calculated here, and the RMS delay spread, which is the key thing here from this graph. Notice here there are little peaks inside the PDP profile, these little small peaks. These peaks show little obstructions. So the peaks are small, so the obstructions might be little. They might not be big. If there's a big obstruction, then there are big peaks shown. So, as we can see, we have calculated the RMS delay spread, which is 3.95. So once the RMS delay spread is calculated, we can simply calculate the coherence bandwidth as shown in this before slide. Once the coherence bandwidth is calculated, we can simply compare it with the signal bandwidth, and for this case, the coherence bandwidth is greater than the signal bandwidth, so the channel is characterized as flat faded. Now, a comment on the large scale fading. It totally depends on the antenna heights and the various types of environment. So if the environment gets complex and the antenna height is varying, if it's large or small, it has a different effect on the large scale fading prospect. Now, coming to the long line of sight, if there are a lot of obstructions between the transmitter and the receiver, this directly affects the delay parameter, which increases when more obstructions and more different types of objects come between the transmitter and the receiver, and the non-line of sight is not there. So the other PDP profile is the industrial indoor channel. It is also similar to the one we discussed before. We can simply calculate the RMS delay value. We can find the coherence bandwidth and compare it with the bandwidth of the signal to have a comment on the channel. The key point in this channel, as you can see, different peaks, but these peaks are large. The last channel had smaller peaks and this channel has larger peaks. So these larger peaks show great obstructions between the transmitter and receivers, and for this case might be big buildings or big objects between the transmitter and receivers, thus the big peaks. And these peaks are not good for your signal. So I hope my video helped some of you guys to understand the basic of PDPs, and some different examples also taught you how to evaluate a channel from seeing the graph and seeing those different parameters. So hopefully you will like the video and subscribe for more.